All right, so this is the second part of section 3.4. All right, let's stop talking, guys. Let's get started. So we're going to talk about solving logarithmic equations. So just again, a quick reminder of the rules that we're using when we're solving these equations. We talked about these on Friday, but it's good to remember because we're going to use them a lot. So a to the x equals a to the y means that x equals y. And log base a of x equals log base a of y. That also tells us that x equals y. And remember, we have to have the same base here. We have to have the same base for our exponential function and our logarithmic function. Our third kind of reminder is.
Wait, did we take this?
We talked about this on Friday, so I'm just giving us a reminder because we're going to be using these same things. Log base a of a to the x equals x. So the logarithmic function and the exponential function essentially undo each other because they're inverse functions. And the opposite is also true. A to the log base a of x power equals x. So these undo each other. So these are our four rules really that we're using, our main rules that we're using when we're solving these equations. So we're going to come up with some steps for solving logarithmic equations like we did for exponential equations. For exponential equations, we wanted to get the exponential function by itself on one side and then either take the log of both sides or rewrite in logarithmic form and then solve for our variable that we were looking for. So we're going to do something similar with logarithmic equations. So the first way that we're going to solve logarithmic equations is get the logarithm by itself on one side. So we're going to get the logarithm by itself on one side of the equation and then rewrite in exponential form. So that's one way that we're going to solve logarithmic equations. Second way we're going to solve logarithmic equations is get one logarithm with the same base and it's important that we remember that we have to have the same base on each side of the equal sign, and then use the rule log base a of x equals log base a of y tells us that x equals y. So that's the second way we're going to solve logarithmic equations. One, we're going to get a logarithm by itself on one side and then rewrite our equation in exponential form. The other way, get one logarithm with the same base on each side and then use this rule And I'm going to say, don't forget our other rules for logarithms. We still need to use those. All right, the phone needs to stop. So don't forget our other rules for logarithms. So we're still using our rules for logarithms. And the last thing to remember is if we get more than one answer, always check your answers. Some of our equations are going to have more than one solution. Always check your solutions. So we're going to check them in our original equation to make sure that they make sense. Because a lot of times when we get more than one answer, one of them or more than one of them won't work in our original equation. We'll get something that won't make sense or that gives us an impossible answer. So these are our steps for solving logarithmic equations. So I'm just going to do a few examples today, just like we did on Friday. Any questions on our process? All right, so let's take a look at a few examples. So we want to solve, on all of these we're solving the equation. So for our first one we have 2 log x equals 5. So we're going to use our first rule or our first process for solving logarithmic equations. We're just going to get our logarithm on one side of the equation. So I divide both sides by 2. So I get log x equals 5 halves. And now I'm going to rewrite in exponential form. So when I don't have a base here, what's our base? 10. So how am I going to rewrite this in exponential form? 10 to the 5 halves equals x. And if I plug this into my calculator, I get x. X is about 316.228 to 3 decimal places. So this one's pretty easy. We just had to take one step. All right, so let's look at another one. We're still solving. So we have the natural log of the square root of x plus 2 equals the natural log of x. All right, this is another one that's pretty easy. So this is using our second rule. I have a log of the same base on both sides of the equal sign, right? So I have natural log of this thing equals a natural log of that thing. So what do we know here?
Square root of x plus 2 equals x.
Square root of x plus 2 has to equal x. And now I want to solve for x. So what do I have to do here to solve for x? Square both sides. So when I square this side, it gets rid of the square root. So I get x plus 2 equals x squared. Bring it over and factor because I have an x squared, an x, and a number. So I'm going to rearrange this and say x squared. I'm going to subtract x and subtract 2 minus 2 equals 0.
Why don't we put the x squared minus
I subtract. So when I'm solving a quadratic, I want to get everything on one side of the equation and a 0 on the other. Now I'm going to factor. How does this factor?
Come down.
x is x minus 2, x plus 1 equals 0. So this tells me x equals 2 or x equals negative 1. Now I get two solutions. I need to check my answer.
Could they both work?
They possibly could both work. So I'm going to check my answers in my original equation. So I'm going to check up here. For the first one, I get the natural log of the square root of 4 equals the natural log of 2. Does that work? Natural log of 2 equal natural log of 2. That's okay. For the other solution, I get the natural log of the square root of, if I plug in a negative 1 here, I get square root of 1 equals the natural log of negative 1. Does that work? This doesn't work. I can't take the natural log of a negative number.
Is that a 4 or what?
This? That's a 4. I'm plugging 2 into this equation. So we're going to throw this one out. And this tells us that x equals 2 is our only solution. So we got more than one answer. We had to check our solution. Questions on that one? Always remember to check when you get more than one solution. All right, let's look at another one. Log x minus log x minus 3 equals 1. So what am I going to do with this one? So, Dominic, what do rules of logarithms tell me this minus sign does? Turns into division, right? Very nice. So this is log x divided by x minus 3 equals 1. Now I have one logarithm on this side. And I can rewrite in exponential form. So I had to use the rules of logarithms on this one. So rewriting this in exponential form, what's my base? When I don't have it, when it's not written there, what's the base? 10. So rewrite this in exponential form, I get 10 to the, what's my exponent? 1 equals x over x minus 3. 10 to the 1 is just 10. So I get x over x minus 3 equals 10, just turning it around. Now to solve for x, what am I going to do? Multiply by x minus 3. Multiply both sides by x minus 3. So I get x equals, and I'm going to distribute here, 10x minus 30. Subtract 10x minus 9x equals minus 30. I'm almost done. X equals 30 ninths, which I can reduce to 10 thirds. So x equals 10 thirds is my answer. So we used our rules for logarithms, and then we proceeded with our regular procedure for solving logarithmic equations. Questions on that example? All right, I want to do a couple of examples next that have to do with our interest formulas. So solving equations that have to do with our interest formulas. So for this one, we have an investment and it is at 8% interest compounded continuously. We want to know how long to double our money. So we have our 8% interest rate. We want to know how long it's going to take to double our money. Well, first off, what is our formula for continuously compounded interest? The amount equals PE to the RT. All right, so let's say we invest P dollars. To double our money, what do we want our amount to be? 2P. So we want our amount to be 2P, so we're going to say 2P equals PE, and our rate is 8%, so 0.08 times T. What can I do with these P's that are on either side? Divide everything by P, and I get 2 equals E to the 0.08 T. So now I have an exponential equation. How do I solve this exponential equation? Switch it to a log form. I could switch it to log form, or just take the natural log of both sides, right? So I can say a natural log of 2 equals a natural log of E to the 0.08 T. Natural log and the exponential function undo each other. So I get natural log 2 equals 0.08 T. And finally, to solve for T, I just divide by 0.8. So T equals the natural log of 2 divided by 0.08. And if I plug that in my calculator, I get approximately 8.66 years. So one thing that's interesting about this is it doesn't matter how much money I invest. No matter how much money I invest, if I'm getting 8% interest compounded continuously, I'll double it in 8.66 years. The initial investment doesn't matter. It'll always double in 8.66 years if we invest at 8% compounded continuously. Questions on that example? All right, one last example having to do with interest. Similar, but we're not doubling our money. We want to get a specific amount back. All right, so we have $50,000. We have $50,000 to invest. We need $350,000 to retire in 30 years. We want to know if we put this in an account or in an investment that's compounded continuously, what interest rate do we need So what interest rate if it's compounded continuously? Possibly. It's a very similar process. So what is our principal here? What are we investing? Okay, how much money?
50,000.
So our principal is 50,000. What is the amount that we want? The amount that we want is 350,000. I need one more zero there. So I'm just going to plug these into my continuously compounded interest formula. I'm going to say 350,000 equals 50,000 times e to the r, and our time is 30. So I'm just plugging that into our continuously compounded interest formula. I'm going to divide both sides by 50,000. I want to get this exponential function by itself. So I get 7 equals e to the 30r. And what do I do here to solve this? Take the natural log of both sides. Natural log 7 equals natural log of e to the 30r. Natural log and the exponential function undo each other. So I get the natural log of 7 equals 30r. So r equals the natural log of 7 divided by 30. If I plug that in my calculator, I get, that's approximately 0.065 or 6.5%. So if I invest my money compounded continuously at 6.5% for 30 years, my investment would grow from $50,000 to $350,000. Pretty good. All right, any questions on these examples? So we're just using what we already know about exponential functions, exponential functions, logarithmic functions to solve equations. All right, homework. Whoops. '61 through 113, every other odd.